Hi everyone. So this is just my quick run through of my part of the oceans topic for paper 3. So the first thing that we need to revise is the biological resources within the oceans that can be used in sustainable or unsustainable ways. And we need to look at the opportunities and threats arising from using this biological resource. So the biological resource that we have studied is krill. Remember, the question is not going to explicitly talk about krill. The question is going to say a biological resource you have studied, and in your brain you need to make the link to krill. That's what we need to talk about. So krill is a natural capita. It is a natural resource that is valuable to humans. We're not manufacturing krill. Krill are there naturally. We can catch them and we can sell them to make money. Actually, using krill is relatively new, catching krill. We've only been doing so since the early 60s. But we need to make sure that we understand how important krill is to the ecosystem of the Antarctic. So the krill is the engine that powers the Antarctic ecosystem. These small shrimp-like crustacea that live about 5 years in the upper part of the water column can go up and down but not against the current. They are so abundant that they have a very special place in the ecosystem. In fact, the biomass of krill is greater than that of the human race. They swim in these huge swarms, up to 2 million tons, that you can see from a huge distance, even from space, as these pink clouds. A huge range of predators feed on krill: seals, fish, penguins, squid, whales. It is the staple part of their diet. So krill is the foundation of the food chain in the Antarctic. We've gone in and we've started harvesting commercially in the Southern Ocean these krill. Krill are then processed into a wide range of products, pastes, their tails are frozen, they're turned into oils, animal feed, bait. They become emulsifying substances that are used in burgers and sauces. It's also seen as a very cheap alternative for shrimp, in particularly important source of protein that could be used for big growing economies such as China, for example, going forward. Currently, only 5 countries harvest krill. Norway is responsible for half of krill caught. In the 70s and 80s, we were concerned that we were going to see a boom and bust cycle with huge, large-scale exploitation that would completely collapse the krill stocks as we reach a threshold where it would be unsustainable for the krill to actually survive, having so much caught and taken away. We've seen this before with whaling, but we're not entirely sure, because we don't have the scientific evidence yet, how close we are to reaching a similar threshold with krill. So we need to be able to talk about the values, attitudes, and political context of the different stakeholders involved in the management of krill. So stakeholders are people or groups or organisations that have a particular interest or concern with the thing that you're talking about. So in this case, krill. So we've got the stakeholders here. We've got the CCAMLR, which stands for the Commission for Conservation of Antarctic Marine Living Resources. That was established back in 1982. There are 24 member states and the European Union. And the governments represent the interests of the stakeholders through their membership in CCAMLR. The aim of the organisation is to balance the demand for krill with the need to maintain the health of the ecosystem. Then you've obviously got the krill fishing companies that come from 5 countries currently. China needs to feed its large population. This is a largely untapped source of marine protein that could be incredibly important in securing their food security going forward. The priority of the fishing companies is obviously profitability and being able to access as much krill as they possibly can. You have got the ARK, the Association of Responsible Krill Companies, who say that they are promoting research and they're facilitating an industry contribution to an ecologically sustainable krill harvest. However, lots of people point out that they're just using words, and actually what they're saying and how they're claiming to be sustainable is based on patchy at best data. Then you've got the NGOs, the conservation focused NGOs like the WWF, World Wildlife Fund, who really want to maintain the health of the ecosystem and see how important krill are as a foundation for that ecosystem. Finally, you've got the scientists, and the scientists recognise that a lot of work needs to be done in order to be able to give an accurate picture of the krill population in the Antarctic, and to see whether the catches that are being taken at the moment have had a significant impact on the health of krill in that wider ecosystem. Most of the stakeholders acknowledge that we need more science, we need more data to be able to fully assess how healthy, how much of an impact we've had on this ecosystem. So you need to be able to talk about the resilience of the resource and key thresholds to initiate management. So we can point out that sustainability is actually an ambiguous concept. The question is, does krill as a species have the resilience to cope with the amount that is currently being caught? So CCAMLR sets this TAC, this total allowable catch, each season, and it's been set at just 1% of the biomass of the krill found in the Antarctic. And the idea is that that will maintain a healthy breeding population and minimize the impacts for the ecosystem. So 1% seems a really small percentage, but that is across the whole of the Southern Ocean. And the concern is that the krill fishermen are not nicely taking their catches from across the whole of the Southern Ocean. They are concentrating what they catch in sheltered locations around islands where they know there will be a dense, predictable krill population to catch. Those areas are also really important foraging areas for predators. So it's felt that actually in those areas, the percentage of krill being taken could be extremely high, nowhere near the 1% for the whole ocean. Some fishermen think that vessel quotas rather than area quotas might be fairer. There's a lot of divided opinion. It's a very contested issue as to whether that management would be effective or not. There are lots of perceptions about the current state of the ecosystem, but it's widely recognised that we need more scientific data to be able to see how healthy the population is. So we're talking about things like sonar surveys of krill shoals, so that we can actually see what is there and how much of an impact we're having. It's clear that krill stocks are decreasing, but there's confidence from most stakeholders that currently what remains is healthy. But we need to see more of a cross-stakeholder management system in place. There are considerable challenges actually policing and monitoring and regulating CCAMLR's total allowable catches. How do you see how much each ship is catching? It's very difficult to see every ship that's out there in the Southern Ocean, and you've obviously got people who are catching krill illegally. We also know that it's not just catching krill that's having an impact on their numbers and on their species. Climate change is also having a big impact. So currently their nursery, their breeding ground, is the underside of ice sheets. But we know that climate change is causing the ice to melt. And if the ice sheets aren't there, they don't have their nursery, they don't have their breeding grounds, and that impacts the number of krill that we have, as well as fishing. So to summarise that, what's small and pink and can be seen from space? Krill, a biological resource, natural capita, a natural product with value for humans. So abundant, these clouds of pink stretch for miles in Antarctic waters, forming the foundation of the Antarctic food chain. Commercial harvesting of krill only began in the 60s and has become a significant industry in the Southern Ocean. Krill is processed into a variety of products, including omega-3 pastes and products, animal food. It's a cheap alternative to shrimp and a huge potential affordable source of protein to feed the growing economies of countries like China. 5 countries harvest krill, including Norway and China. No LIDCs are involved. The concern of the 80s was that there would be a boom and bust situation with large-scale exploitation leading to the collapse of krill stocks as the threshold for sustainable fishing was exceeded. Management was therefore required. CCAMLR has 25 member countries. Its aim is to manage and regulate commercial interests within a sustainable ecosystem. As such, they attempt to manage krill fishing by setting a total allowable catch limit at just 1% of the total krill biomass per year. Surely this management measure will ensure a sustainable krill population remains and will therefore be seen as sustainable. Surely any population is resilient enough to cope with 1% being removed per year. However, in reality, krill catches are not spread out nice and evenly across the ocean. Fishing is concentrated in sheltered locations around islands where catches are dense and predictable. It is also extremely difficult to police a vast stretch of ocean, so illegal krill catches are common. This being the case, we are not confident in the overall percentage of the total biomass being caught. It is also clear that in some areas the threshold for maintaining a sustainable krill population is being exceeded. The main objective of krill fishermen is to make as much profit as possible. The Association of Responsible Krill Fishermen claim to be acting sustainably and managing their catches within a threshold. However, these claims are based on patchy at best scientific data and therefore wildly misleading. Conservation-focused NGOs such as Greenpeace continue to campaign for the removal of krill-based products. Holland and Barrett has, as a result, removed krill-based omega-3 products from its shelves. This highlights the success these powerful NGOs have. In reality, it's not just fishing that threatens krill stocks. Climate change is undoubtedly also reducing the number of krill. Krill nurseries are found on the underside of ice sheets. In a warming climate, these ice sheets are melting, removing these important breeding grounds. This being the case, any successful management would have to target both fishing and the warming climate. CCAMLR backed the proposal for an Antarctic sanctuary, 1.8 kilometres squared of protected ocean. Research clearly shows areas of ocean that are left alone are incredibly resilient, with ecosystems once again flourishing as a result. Unfortunately, China, Russia and Norway opposed the proposal, concerned about the economic impact it would bring. CCAMLR vowed to keep fighting for the sanctuary. There are a wide range of opinions about the current state of the ecosystem, but it is widely recognised that we need more scientific data on which to base an assessment about the health of krill as a species. Such accurate and reliable data is more readily available today thanks to increased technology in the form of sonar surveys. It is clear that krill numbers are decreasing, and although all stakeholders believe the species is resilient enough for now, there is little agreement as to where the threshold lies, beyond which krill becomes a threatened species. History tells us that even huge populations can be driven to the point of extinction, for example the passenger pigeon. All agree that there needs to be more cross-stakeholder management. The management of krill in place currently is successful to an extent. However, clearly more needs to be done to ensure the survival of krill as a species. Krill might be tiny, but to protect the biggest creatures in the ocean, we need to start small and think big. We also need to be able to talk about the opportunities and threats arising from the use of ocean resources. So this includes oil and gas, and then wave and tidal energy. So we need to be able to talk about both non-renewable and renewable. So in terms of non-renewable oil and gas, we've actually only been drilling for oil since the end of the 19th century. We started out from the edge of piers, and then in the 30s oil rigs, and since we've gone into deeper and deeper and more hostile waters. Since the mid-20th century, increased demand has led to increased exploration and production. And we're now right out to the edge of the continental shelf. There's significant production in the Gulf of Mexico, the Persian Gulf. Price fluctuates greatly due to changing supply and demand. But in order to extract oil and gas from the ocean, we need significant infrastructure. We need pipelines, we need storage tanks, we need refineries. The super tankers that we use to transport oil around the world today are so large they need 30 meters depth and 2 kilometers stretch in order to be able to even turn around. Positives of this industry is it creates jobs, it creates wealth for the countries that are able to extract this from their continental shelves. You've got raw materials to create a wide range of products, fertilizers, paint, plastics, which then enables a higher standard of living. The oil rigs do actually become artificial reefs and support populations of, for example, the fish red snapper in the Gulf of Mexico. Negatives are the local communities become overly dependent on this one industry for jobs. Then you've got the issues of noise, stirring up the seabed, disturbing the ecosystems, visual pollution, and the potential for oil spills. One example of a place where we've got a big oil and gas industry is the Gulf of Mexico. The undersea geology is rich in hydrocarbons, and they're drilling further and further and deeper. There's 140,000 kilometers of active pipelines crisscrossing the ocean floor. But you've got a huge number of jobs and services, and it's had a significant socio-economic impact in that area. Then you've got the use and management of renewable energy from the oceans. So we've got wave and tidal energy. So wave energy is where you convert the rise and fall of the waves into energy. The potential for this is huge and greater than tidal energy. However, for this to be effective, you need to have high wave energy. And in locations where you've got high wave energy, for example, the west coast of the British Isles, the devices that we've been able to produce so far to try to capture this energy haven't been able to survive the rough seas. In order to make them more robust, you have to make them heavier and bigger, and that reduces their efficiency and means that they become uncost effective, and there's no way we can actually use them effectively. There are several examples out there that are being worked on. You've got Polaris, which is an elongated steel tube, still some way off being viable. But you've also got buoys and floats that people are trying to use to harness the energy. As yet, no commercial system has been developed. Then you've got tidal energy. Both wave and tidal energy are flow resources, so they have to be used when or where they occur. It obviously comes, the energy, initially from the sun's energy and the gravitational pull of the moon and sun, creating the tides. So you try to harness the rise and fall of the tide twice a day in order to use tidal energy. There are very few large-scale schemes that have been built. There's a huge potential, but you have to have the correct local physical geography. So you need to have the shape of the coastline that works. You need to have a large tidal range, so the movement of water in and out twice a day is big enough to generate energy. The pros are the tides are regular, they're reliable, they're predictable. Most coasts have 2 a day, 2 high tides, 2 low tides a day. The cons are there are many suitable locations, but few of them are close to where there's actually a high demand for electricity. And there's an economic limit to the distance that we can actually transmit and transport this electricity we're making to actually justify the huge cost of the development. So one scheme that was proposed was the Swansea Bay Tidal Lagoon, where they were going to enclose 11.5 kilometres squared with 16 turbines spinning using the tides around Swansea Bay to generate power for 155,000 homes. The advantages would have been renewable energy, 16 out of 24 hours a day, low carbon emissions, a very small carbon footprint across its lifespan of 120 years, local employment would have been created to construct it and then to maintain and operate it, and it also would have created a lovely recreational area with tourism opportunities, a cycle path, fishing, visitor centre. The concerns were that it would interfere with sediment movements in the bay, that it would slow the movement of water, which would perhaps lead to poor water quality, disturbing habitats with noise and vibrations. And Swansea Bay is a really important site for migrating birds that pass through. So some environmentalists said you shouldn't carry out a giant experiment using public money in such a sensitive environment. Eventually, this scheme was shelved because it turned out that it was increasing in cost, and the government decided that it wasn't cost effective, and so that scheme was shelved. Okay, so to summarise, using oil and gas, non-renewable. So we've only been drilling for oil since the end of the 19th century, first from the end of piers, then in the 30s from oil rigs, and more recently into deeper, more hostile waters. Since the mid-20th century, demand has increased, and as a result, exploration has increased, and production is now out to the edge of the continental shelf. There's significant production in the Gulf of Mexico and the Persian Gulf. The price of oil fluctuates greatly relative to changes in supply and demand. A significant infrastructure is needed. Pipelines, tanks, refineries, supertankers today are extremely large. Positives: jobs are created, wealth is generated, raw materials for a wide range of products are produced. Oil rigs become artificial reefs and increase populations of, for example, the red snapper fish in the Gulf of Mexico. However, local communities become overly dependent on one industry. Noise stirs up the seabed and disturbs ecosystems. Visual pollution, oil spills. So long term, we need an alternative source of energy to address the issues of diminishing supply and carbon emissions that contribute to global warming. So we look at wave and tidal energy as flow resources. They must be used when or where they occur, naturally generated by the sun's energy and gravitational pull of the moon and the sun. So you're converting the rise and fall of waves into energy. The potential for energy from the waves is huge and even greater than from the tides. However, you need to have high wave energy. And these locations, you cannot get devices to survive the rough seas. If you make them bigger and more effective against the conditions, they become inefficient and ineffective. Tidal energy, you have huge potential depending on the physical geography and the tidal range. The tidal range needs to be very high. Tides are regular, reliable, predictable. Many suitable locations, but very few are close to where you've actually got a demand for the electricity. And there's an economic limit to how far you can transmit it cost effectively. And then you've got the Swansea Bay scheme you can talk about. We've also got mining from the seabed that we need to be able to talk about. So mining for ferrous, which means iron, and non-ferrous, so doesn't contain iron, minerals. So ferrous would be steel, non-ferrous would be aluminium, copper, that kind of thing. So we are increasingly interested in seafloor mining. The growth of the rare earth elements, or REEs, for electrical technology also known as the seeds of technology, which actually allows us to produce miniaturized electronics like mobile phones and support telecommunications and defense systems. And these particular elements have unique magnetic, phosphorescent, catalytic properties and are irreplaceable in the technological world. Also really important for military hardware like missiles. Rare earth element production is dominated by China, 85%. Other countries are concerned that they will create a monopoly and prevent them having access to mine certain areas of the sea floor. So they use deep remotely operated vehicles to survey and sample the seabed, and then they use these hydraulic suction systems like giant vacuums to suck up the minerals, to suck up the metals to mine them. So the concerns are that this mining is focused on mid-ocean ridges and hydrothermal vents, and given the lack of knowledge we have about these ecosystems, it's hard to assess the potential damage, but we could be doing a severe amount of damage to these sensitive locations. Many of these oceanic minerals exist in greater concentrations than they do on land. So land copper ore is 4% metal content. Some seabed copper ore is 10 times more concentrated. So you could argue that less needs to be mined to obtain the same quantity. However, when you mine the seabed, you create waste. You have to suck everything up and then you throw back what you don't need, and that's called the tailings. When you release that back into the ocean, you make the water cloudy, the light is less able to penetrate, that material settles on the seafloor and can smother the seabed ecosystem. However, mining companies are adding to our knowledge of our understanding of the deep oceans. It is a highly contested issue. We are likely to see increased demand as we advance our technology, which is going to put increased pressure on seabed environments. Others argue that the mountains of the Pacific underneath the ocean alone could have 22 times more tellurium that's used in solar panels than we have in land-based resources. So an argument that these minerals will help us to produce renewable energies going forward and reduce our need for non-renewable oil and gas. There are potato-sized nodules of metals covering the sea floor, for example iron, across submarine mountains. The mountains are essentially coated in minerals that can be broken into pieces and then vacuumed up. You've got manganese nodules that are slow growing on the ocean floor, and they develop when dissolved minerals crystallize around a small particle. We have to balance the need for resources with the need to preserve ecosystems for future generations in order to be sustainable long term. So again, you could stop and just have a little look at the recap there that you've got. Then we've got how and in what ways do human activities pollute oceans? So we can talk about the combustion of fossil fuels, CO2, sulfur dioxide, nitrogen oxides, particulates. Ships rely on fossil fuels for power. Heavy ships go long distances, and actually the total emissions from ships are significant on a global scale. There are 100,000 cargo vessels on the world's oceans 24 hours a day, 280 days a year on average. The engines use low-grade oil that is very high in sulfur, and the largest emit 5,000 tons of sulfur per year. Overall, shipping is responsible for 9% of sulfur dioxide and 15 to 30% of nitrogen oxide emissions that we have in the atmosphere. So 3.5 to 4% of greenhouse gas emissions from human activity actually come from shipping. Most shipping pollution occurs in the northern hemisphere because this is where the busiest routes are. Locally, this is concentrated in and around the major ports. Air pollution there can be a serious hazard. Then we've got the increased use of cruise ships, and those cruise ships are going into small inlets. So, for example, the Alaskan fjords. They're using fuel that's high in sulfur, and they're concentrating their pollution in and around those small inlets. There are things that are being looked at to try to reduce the amount of pollution from shipping. So reducing speed reduces the amount of fuel used, reduces the amount of emissions. Looking at using kites and sails so that these ships can harness the wind's power when there is sufficient wind for them to do so, and they could actually turn off their engines for a time. When we actually look at pollution as a definition, it's when human activity adds a substance to the environment that affects organisms adversely and at a rate greater than at which it can be rendered harmless. So domestic and industrial pollutants includes plastics, heavy metals, nuclear waste. Where are the sources of these pollutants? So you've got fertilizers that farmers have put on their crops, and they put the fertilizers on their crops to make their crops grow big and strong. The rainwater washes the fertilizers into water, into rivers and lakes, where it causes the algae to grow big and strong. And all of that algae then blocks out the sunlight. The algae that's lower down in the water dies. Dead algae feeds the bacteria, which leads to aerobic respiration by decomposers, which then removes oxygen from the water. And without oxygen in the water, the fish die. We have examples of harmful algal blooms that take place, for example, in California, up towards Alaska in America. These harmful algal blooms produce acids that accumulate in the shellfish. Then the seabirds eat the shellfish and it poisons them. Can also make humans ill when they eat these shellfish with these toxins in, and it has an economic impact on the fishing industry. Then you've got nuclear waste. So, for example, following the tsunami in Japan in 2011, there was a leak of nuclear waste from the Fukushima nuclear plant. That radiation gets into the food chain, so they had to have a ban on catching or consuming fish or shellfish from around the Fukushima region directly after that 2011 tsunami. However, the oceanographers found that it had little threat to the Pacific Ocean as a whole. The serious risks were very local in scale because the pollution was quite quickly dispersed amongst the big body of water in the Pacific. Then we've got plastic. So plastic enters the oceans from the rivers. So people drop plastic waste, it rains, the rainwater washes the plastic into the river then brings everything down to the sea. And that's where a greater majority of the plastic waste comes from, into the oceans. You've also got people leaving stuff on beaches and things that are being dumped off the side of ships at sea that go into the ocean. And then if there's a storm and a ship is carrying lots of cargo, that cargo can be discarded accidentally into the oceans as well. Plastic is extremely persistent. It doesn't biodegrade. It simply breaks down into small pieces as a result of photodegeneration, which is where sunlight acts on the polymer chains. All plastics start life as these tiny nurdles. These are shipped around the world, these tiny nurdles, and they fall off ships. And so they've been washed up and are found on beaches all around the world and in every ocean. A 2016 report predicted that by 2050, plastic will outweigh fish in the world's oceans. This plastic gets spread around the oceans by ocean circulation. And we sort of discovered this with the help of a 1992 container that discarded thousands of plastic bath toys into the Pacific Ocean just northwest of Hawaii. Ducks, turtles and frogs, bath toys, spread then all around the world's oceans. which really gave us a very good understanding of ocean currents. 28,000 toys travelled 17,000 miles. Some of them got caught in the subpolar gyre and took 10 months to start landing on Alaskan shores, right up in Alaska. Some found their way to Hawaii, the Arctic, northwest Scotland. And this perfectly illustrates how marine pollution can spread right around the world from its source point. And we know that we've got these ocean gyres, these large systems of circular ocean currents that are formed by global wind patterns and created by the Earth's rotation, or the Coriolis effect. So a plastic bottle that's dropped off the coast of Shanghai in China is likely to be carried east by the North Pacific Gyre and end up circulating a few hundred miles off the US coast. India is one of the world's biggest plastic polluters. It's likely that that pollution gets caught in the Indian Ocean Gyre and concentrated in the Bay of Bengal. Basically, what you end up with is a marine rubbish vortex created by these gyres. So this is a summary of what we've just talked about. So what is pollution? And then you've got your combustion of fossil fuels. You've got your domestic and industrial pollutants like fertilizers, nuclear waste, and plastic summarized there. Then you've got your bath toys that we've just talked about. So what is the impact of this plastic pollution on marine ecosystems? So plastics become wrapped around animals like seals and turtles, which can strangle them and which can cause them to drown. Smaller pieces of plastic are ingested by fish and birds, which disrupts their digestion and gets into the food chain when bigger animals eat those smaller animals. Plastics are so persistent, items from the 40s, the 1940s, are being discovered in seabirds' stomachs today. Plastic is found in 90% of seabirds. They eat it thinking it's food, and then it blocks their gut and the chemicals build up in their tissues. One idea is if we could create plastics that don't accumulate as much algae, they might be less likely to be eaten by seabirds. Some of even the deepest creatures in the ocean have been found to have eaten microscopic plastic. A study of Rockall Trough has shown us. This plastic is everywhere throughout the ocean from top to bottom. Cleaning up is an interesting thing to look at. Cleaning up the oceans could do more harm than good. If you're going to sweep up the plastic from the ocean, then you're going to inadvertently sweep up plankton as well as plastic. So you're taking away the basis of the food chain. You're taking away the phytoplankton that is responsible for half of photosynthesis on Earth at the same time as scooping up this plastic. As long as countries lack the ability to efficiently collect rubbish from their citizens, that rubbish will end up in the ocean. Plastic itself is not the problem, it's how we dispose of it. So we need a case study of the accumulation of plastic in the North Pacific Gyre. So the cause of this accumulation is the North Pacific Subtropical Gyre, which is created by the interaction of the Californian, North Equatorial, Kuroshiro, and North Pacific currents. These four currents move in a clockwise direction around an area 20 million kilometers squared. This circular movement of the gyre allows the debris to be drawn into the calm, stable centre where it accumulates, as most of it is not biodegradable. This is not just on the surface, but you've also got microplastics that make the ocean look like a cloudy soup, and the sea floor is also covered in rubbish. About 80% of the debris here comes from land-based activities in North America and Asia. 20% comes from boats and ships. The largest patch is between Hawaii and California. Plastic that was washed out to sea after the 2011 Japanese tsunami could account for as much as 20% of the plastic that accumulates in this patch. As the Great Pacific Garbage Patch is so far from a coastline, no nation will take responsibility for funding a cleanup. A cleanup of this great big massive patch could bankrupt a country, and it's clear that international organisation is needed to tackle this issue. Cleaning up just 1% of the North Pacific would take 68 ships working 10 hours a day for a year. That's just 1%. That's according to NOAA. Loggerhead turtles mistake plastic for jellyfish, which is their favourite food. The albatross mistake pellets for fish eggs. Seals get entangled in plastic bags and abandoned nets. Plastic at the surface blocks the sunlight reaching the plankton and the algae below. Plankton is threatened, which therefore threatens the entire food chain. So it's a massive, massive issue. So just got a summary there of the causes and the effects for the ecosystem, for the biosphere of that Great Pacific Garbage Patch in the North Pacific Gyre. So that is my summary of my half of oceans. You now need to look at the remaining part of oceans, and you also need to do your disease revision.